In this video, I want to look at a phenomenon that we have with optics, and this is thin film interference. So this is kind of an interesting random bit that I know you've kind of seen, and we'll get to an example of that shortly. So thin film interference. We've talked about light and how it interacts with materials, and in all materials, they always reflect a little bit of light and allow some to pass through. So this is true for basically everything. Even if it looks perfectly reflective, some of the light is being absorbed or passed through, stuff like that. So if something is clear though, or like appears more translucent, that's just because it's letting more light pass through than it's reflecting. If something looks really shiny, it's reflecting more than it's absorbing or passing through. So if a material is thin enough, then the light reflected from the top and bottom of that material can interfere with each other. And what does that look like? Well, that would be like this. So if I've got a material, so imagine this is a side view. I've cut it away. So now a piece of light coming in like this, some of it will get reflected off. Some of it will travel straight through, bounce off the bottom, and then get reflected off here. I've separated them out, but in reality, if it's thin film, these two lines are basically right on top of each other. So in other words, the light going through the bottom and the light going through the top kind of come back together. But because it had to travel a certain distance in here, those light waves are no longer lined up, so they interfere with each other. So that gives us a bunch of different results. You can have a shiny appearance. And this is if we have nearly perfect constructive interference. So in other words, if basically one wave passes by the time it goes through this and comes back, or two waves or stuff like that, then when they line back up, it'll make it brighter. So thin film interference can make something be really shiny if we're getting a lot of light constructively interfering. We can get a dull appearance if we have nearly perfect destructive interference. So in other words, if the light bouncing off and the light that goes through here, if they destructively interfere, it'll make the reflection dull. And I should say these are the reflections. So a shiny reflection or a dull reflection. And then the most interesting, we can get a rainbow appearance. If there are slight differences in the thickness as you go along, so if it is something like this, again, this will be on like the very microscopic scale. If we've got something like this where it's thin the whole way, but it's different thicknesses as you go along, right? It's this thick, then it's a thin, then thick, and then thin. Then those different thicknesses will mean that only certain colors of light or certain wavelengths of light constructively interfere at a given point. So maybe right here you get red interfering, here you get purple, here you get green. And so that means when you look at it, you see, this is redder, this is greener, this is bluer, etc. So let's talk about some examples. The first is sort of what we would call like radar cloaking. So if people are trying to detect something by shooting out light waves and then detecting when they bounce back, so using like infrared or ultraviolet, stuff like that, then what you could do is hide something from that by making sure that the light that bounces into a thin film that's covering something destructively interferes. So if I put like a thin film just on the edge of, a wall or something like that, or if there's an opening in the wall and I put a thin film up, then maybe the light that's bouncing off of the outside of that film and the light that's bouncing off the backside, if they destructively interfere, then the light will basically pass through and won't bounce back to the sensor, and whatever was sending out the signal will think, oh, there's nothing there, because the light I sent out never came back. So that's what we want to have, because the sensor works by sending out light, having it bounce back, and saying, oh, there's something this far away. But if we can get those to destructively interfere, it'll think the light just went on and never bounced back, therefore nothing is there. So you can like hide things from these types of sensors. Now that obviously won't work visually because we have a wide visual range, so maybe we could get it to not, like we could get certain wavelengths to disappear, but we can't get all of those to disappear. This radar cloaking works off of the fact that typically a very, very narrow band of light is being used to detect things. Just a very short thing, so you can get this to kind of come into effect. The other way that you can overcome this that isn't thin film interference is you basically just have it bounce off at weird angles and not bounce straight back. So by having things very jagged, or conversely very smooth, but in a way that you don't ever get straight surfaces back to wherever they might be sending it. The more common example will be an oil or gas slick. So if you've ever seen like liquid on the ground, and then you see, you know, rainbow kind of rings or shapes in it. So you've got, you know, a red, and then you've got kind of all these colors showing up in it. That is from thin film interference, and that's that rainbow, quote unquote, option that can happen. So basically what ends up happening is along, like we said, the surface, it's got varying thicknesses, because naturally just as it lays out across water or across concrete, certain parts are going to be slightly thicker, slightly thinner, and you don't need a huge difference for this to happen. But what ends up happening if it's on top of water, well then, you know, the light comes through, some of it bounces off the surface, some of it bounces off the bottom, and especially if you've got water below it, because you're going to have a tendency to get total internal reflection, or the same type of thing that we'd have for total internal reflection off of the water surface, but not off of the light surface, or the air surface. And then basically you just get different frequencies interfering constructively based on the thickness. So when this thickness is about half the distance of a wavelength for red light, well, by the time red light travels down and comes back, a full wave is passed, they constructively interfere, you get this part appearing more red. If this part is, you know, half of a green wavelength, well then by the time it gets down and bounces back, then the green is interfering constructively. And you continue this all over and you just get sort of random colors all over the place. But you do end up seeing generally rainbow because the thickness is going to be thicker and thinner. So that means when it's thinnest, it's going to be constructively interfering with blue lights, wavelengths that are really short. As it gets thicker, it'll go up to red. And then as it thins back out, it'll go back out to blue. So that's why you do still get sort of those organized ring type shapes and stuff like that. And it still looks rainbowy as opposed to just random colors flashing, is because of that general increase and decrease and all of that. So let me know if you have any questions about these phenomena. Otherwise, that will wrap us up here.